Welcome back to another section on radical functions. Power to the equations. This section we're going to be looking at functions, which would be the graphs of these radical functions, and also we're going to hit transformations in this section. Now we've done transformations a lot at this point, so it's going to be a very, very quick reminder of transformations, but it will not be the typical transformation thing which lasts the whole time. So let's take a look at our learning targets. The first one, I can graph radical functions and inequalities. They're basically the same. I'll mention inequalities right at the end. And then I can transform radical functions by changing parameters. That would be the transformation part of it. And so we're going to take a look at two different types of radical functions. Now these are two types of functions in the same family that are very different. They're like the Montagues and Capulets if they were radical functions, except that these are from the same family and not fighting with each other. So they're really nothing like the Montagues and Capulets, but they are just a bit different. One type would be the even roots. That would be square roots, fourth roots, sixth roots, things like that. We're really going to focus with square roots. We don't even get up to fourth roots very often, so square roots will be what we have here. And odd roots. That would be cube roots, fifth roots, seventh roots. We'll stick with the cube roots on these guys. And so if we look at the even roots, f of x equals square root of x, odd root, f of x equals cube root of x. The first thing we want to look at is a graph. If we were to graph this, we'd start out with a table, and we'd plug in some points. X equals 0. Well, the square root of 0 is 0. X equals 1. Square root of 1, 1. Not very exciting yet. But now if we went up to 2, the square root of 2, well, it's 1.4 something, something, something. Nobody cares. Square root of 3, 1.7. No. What's the next number that we can take a square root of nicely? 4. The square root of 4 is 2. And now we could think of what's the next number we could take a square root of, which isn't all that hard to think of. Or we can say, hey, look, 0, 1, 2. I bet the next number is going to be 3. Well, the square root of what's going to equal 3? 9. And so we have some points. We can graph them. And notice we don't have anything less than 0 here because you can't take a square root of a negative number and get a real number. You get imaginary numbers. We don't care about those at the moment. So it has a very distinctive starting point. And because of that, it has a domain and a range that's limited. The domain, x, has to be greater than or equal to 0 because it can't be negative. And the range, well, since x has to be greater than or equal to 0, y will also be greater than or equal to 0. So we have our domain and our range there. With the odd roots, we can do the same thing. Get a table, 0, cube root of 0, 0, 1, cube root of 1 is 1. Now we don't go up to 4. What's the next number we can take a cube root of? That would be 8. The cube root of 8 is 2. Now we can think, all right, so 3. Well, what cubed, or what the cube root of what would give us 3? Well, that would be 3 times 3 times 3, which is 27. See, these guys get big really fast. And so we have these numbers. But with cube roots, we also have the negatives. Negative 1 would equal negative 1. Negative 8 would be negative 2. Negative 27 would be negative 3. And so we get both the positives and the negatives. And so the graph continues. Now, if you look at the graph, and right now I'm covering up this piece of my monitor with my hand because that's effective, it looks like a square root right here. And then we just have another piece of a square root. And that's what it looks like. It does get a little bit skinnier. Notice it's zoomed, well, actually it's not zoomed out a bit. But here at 8, it only gets up to 2. Where here at 8, it gets all the way up to almost 3. And then So square root looks like this, odd root looks like this. A fourth root would look a lot like the square root, except it would be even squishier. We'd have 0 and then 1, and then it would be at 16 when we got to 2. So it would just be smashed down a little bit. And then sixth root, it would be smashed a bit more. It's not really a smash, it's more of a horizontal stretch, but it's kind of what it is. And then same thing with the odd roots. It just gets, the fifth root would be skinnier, it would be flatter, and it would go both directions. You can graph them in your calculator if you're really concerned about what they look like, but these are the two shapes that our roots have. Even roots look like this, where it has a starting and stopping point. Odd roots look like this, where there's no starting and stopping point. So the domain, well, it could keep going both directions. So the domain is all real numbers. And the range, well, since the x can keep going, means the y is going to keep going, it's all real numbers. And you might be thinking to yourself, just the other day, Mr. Swanson said that the domain is not just a number. It's like x equals something, x is bigger than something, x doesn't equal something. But here he put all reals, and that's it. All real numbers is the exception. You don't say x equals all real numbers. That's just kind of weird. And this is shorthand. If we wanted the really official deal, it would be in set builder notation like this, where the domain is x such that x is x is an element of the set of all real numbers. But that's just a bit ridiculous. We just shorten it to all real numbers. So that is the exception. It's not a number, it's all numbers. And so these are what they look like. Now we can do some transformations with these. When we do transformations, we can have all of them. We're going to stick them all into one big equation. G of x equals a times the square root of 1 over b times x minus h plus k. Now here, and now this is a times the square root. This is not the eighth root. This is just a square root. And I chose square root. It could have been cubed root. It could have been fourth root. It does not matter what this root is. None of our transformations are going to change this root. It is going to stay the same as whatever it happens to be in the beginning. The transformations are going to do the same thing for each of them. This a value, the number that's multiplied to the function, is a vertical stretch or compression. It's going to pull it up, smash it down. Here it's going to pull it up or smash it down. And if a is negative, it'll be a vertical reflection. Instead of being up here, it would be this half of it. It would end up looking like a sideways parabola if we had both pieces. And we'll get back to that in a future chapter. Over here, it would flip, where it would be start up here and then come down and go this way for a vertical reflection. B is a horizontal stretch or compression. It's going to squish it towards the y-axis. Also, if b is less than 0, it's a horizontal reflection. So instead of going this way, it would start here and go this way and be all negatives. This one would flip, and a horizontal reflection, a vertical reflection for an odd root are actually the same thing. So it's kind of fun. It just switches from being a positive and negatives to being a positive, negative, positive for the x and y. The h is a horizontal translation, and the k is a vertical translation. And what that does is it would take this point and just move it. If we wanted to move it to the right 4, we'd have x minus 4 under the square root, and we'd just move it so the point was right here. If we wanted to move it over 4 and down 2, we'd move it so the point was right here. And if we moved it over 4 and down 2, that would be x minus 4 underneath the square root, and then minus 2 on the outside. Here, we would take this point in the center, which is, it's not quite as distinct as this point, which is the beginning, but it is still a fairly distinct point. And we just move it over. So our little S piece of this, the vertical piece, would just move to whatever point we're looking at. And since we're moving this, that'll change the domain and range. The domain will change with the horizontal translation. The range will change with the vertical translation. And so the domain will just be x is greater than or equal to h, and the range y is greater than or equal to k. A vertical stretch or compression won't change the domain or range. A reflection will. A reflection would switch the sign. So if it was a horizontal reflection, it would be x is less than or equal to h. And a vertical would be y is less than or equal to k. Over here for the odd roots, we have all real numbers. If we move it over, we still have all real numbers. If we reflect it, we still have all real numbers. So the domain and range will stay all real numbers. It's not going to move. And so this is the transformations. I thought about throwing some examples on here, but we've done transformations a bunch. And so I don't have any examples on here, but we will have some in class. The last thing is inequalities. With the inequalities, it'll be y is greater than or less than the root with whatever. Well, if it's less than, you'd shade below. If it's greater than, you'd shade above. If it's or equal to, it's solid. If it's not or equal to, it's a dotted or dashed line, the same as it's always been. The big difference is with an even root, the square root. If we had f of x is less than or equal to square root of x, we'd shade below. But we'd only shade below in the domain. We'd shade below over here. We wouldn't shade over here where the function doesn't exist. Only when x is greater than or equal to 0. So we'd shade there. And same thing if it was greater than. We'd shade above, but only for when x is greater than or equal to 0. For cubics, doesn't matter because it's all real numbers. It's just the whole bottom or above. Anyway, that is the topic. That is 8.7. It's stuff that we've done before. The graphs are a little bit different. We'll have domain and range questions in there, but the transformations, which is a majority of it, is exactly like what we've done over and over and over again. So we'll see it again, and we'll have some examples in class as you'll be working with your group, and I will see you then. Enjoy.